imaging, right? The stars are crowded in the actual image, but these galaxies are not crowded in variable stars. So you can identify variable sources very cleanly. The problem is getting their mean flux, because then you suffer from the crowding of the ground-based resolution. And basically, we look at everything that varies by more than 10 to the 4 solar luminosities. And basically, everything except the Wolf-Rayet stars, which you think will explode, has an optical luminosity above 10 to the 4 solar luminosities. OK, so this is the sort of galaxy you're looking at. That's M81. OK, so that basically shows you the field of view. You get all of M81 in one shot. And the first thing you get is you get lots and lots of false positives, because, of course, the world is mainly filled with false positives. So this is an example of a subtraction artifact. I should say what you do is, so remember, in difference imaging, what you do is you take a whole bunch of your good images and you construct what's called a reference image. So this is this reference image. And then you subtract that from all of the other images, so you see how it is changed relative to the reference image. And so these are all these subtractions from first to the last image. Okay? And then what you can also do is you can construct the RMS of a galaxy. In fact, at one point I even constructed the Fourier transform of a galaxy. And so basically this is the variable signature. Okay? And so this says there's a variable source there. Here's the sort of sequence of, that's the first image, there's the last image, there are subtractions. And if you see these little dipoles, you're probably going to say, yeah, that doesn't look very real. And the answer is it's not real. It's a common subtraction artifact around bright stars. There are asteroids. I don't know why anyone put asteroids up there, but they're there. In Assassin, I counted it up once. We have something like 1 million observations of asteroids that have been flagged in Assassin.
And nobody's following them up.
No, well, they've been a little bit of use for it, but it's not, it's not our stuff. So.
Yeah.
But Matt Holman predicted when we started that we would never find a new asteroid, and so far he is correct.
1 million old asteroids.
Yeah, it's not a million individual. It's like 50,000 individual asteroids, but a million. Okay, so this is an asteroid where you can sort of see you get the track because the thing moves while during the exposure. Then you get sort of variable stars. All right, so you got to go through and eliminate all of those. It's a little tedious. All right, so this star would periodically give us a little frisson of excitement because here's the reference image. Here's something that's variable. Here's the first image. There's the last image. And I've set it up, actually, when I've reconstructed this, is so basically this was constructed from all of the pre-event images. And so pre-event, it basically subtracts. And in here, I have excised the vastly saturated image of taking pictures of a nearby supernova with an 8-meter telescope. And then here's afterwards. And what's happening is you're seeing a negative image of the progenitor appear as the supernova fades. Okay? And so this is the signature of a star which died, okay, albeit a negative, is I start with a star and I end up without a star. Okay? In this case, I happen to know what happens because this was a supernova 2011 DH. And so we know there's a supernova inside. But our methods for trying to find failed supernova would keep flagging this one, and then you say, oh, that's that thing again. And so this is roughly 100,000 solar luminosity, yellow supergiant. Most of the scenarios for this depend on binarity and things. But it turns out it's hard to get more examples of this because it turns out it takes these supernovae a really long time in general to fade to be fainter than their progenitors. It's painfully long. It's like 3 years later, and they're still brighter than their progenitors.
Chris, in our galaxy, there are these strange stars. One of them is Tabby star that change brightness because of perhaps occultation or something. Are these confusing?
Well, but remember, the amplitude of that is negligible, right? It's not very big. So
tens of percent.
Yeah. So the problem is we don't really know of stars which can change their luminosity by a factor of 100 4 timescales of a decade. Right? So here's this particular object. Is we can track its luminosity at sort of 100,000 solar luminosities back to about 10 years before it had this weak transient. Okay, and then faded away. Okay, and since then there's sort of been no variability. Okay, there's some issues with exactly how you get to zero. So the fact that this seems to be at 5,000 doesn't mean anything. But you can sort of see is it was at 100,000. It went up to a little bit above 10 to the 6, which is consistent with this Nadesian scheme. But we don't have proof that that is what happened. Unfortunately, we did not get a spectra of this, but it looks very much like that. and then it faded away. And, you know, you can go back with Hubble. It fortuitously had some Hubble observations from actually only a few years before the transient event. And so there it is in V-ish and I-ish. Okay, here it is in 2015. I think we can safely say that somewhat has gone away. Okay, and then there may be a weak infrared source there, which would not be crazy because there should be some late time accretion, and you should have made dust, so it's not obvious that you should see anything in the optical. And we did also look for X-rays, and we did not detect X-rays. But that was a real fishing expedition, because if we had found X-rays, you would know what had happened. But if you don't find X-rays, it's trivial to not see X-rays just from the debris. So anyway, we were even honest. We said this was a fishing expedition. They gave us the time anyway. And so here's it's fading away, and we actually have another point, which is down around here. And that power law decay is characteristic of some models of late time accretion, although again, it's not something I'm going to bet my life on. All right, if you ask what the star was, it was a 20 or 25 solar mass red supergiant, sort of exactly in the bin where I've been arguing you ought to be looking for these things. So that all looks nice. All right, so here are the implications. If you think it's real, then the collapse rate is, the failure rate is about 14%, with big error bars because it's only statistics of one. But as Andy Gould likes to point out, is you can do statistics with no objects. So one is a major improvement. If you say there are no such things, it's the upper limit is 35%. If you don't want to believe this. This is it's peaking exactly in the regime where you would want to explain the black hole mass function or the missing red supergiants and all of that. So it all at least hangs together very nicely. This is the sort of limit you'll get from 30 years of not finding galactic neutrinos, okay, from a failed supernova. Okay. So you can do some other things with this data. As in particular, you can look at progenitors. And so again, this is 11DH. And so one thing you can get is if you can wait long enough for the supernova to fade, is you can do very good photometry of the progenitors. As I said earlier, is there are very few progenitors which have good photometry. Okay? In theory, is once the supernova fades, through this magic of difference imaging, we have UBVR photometry of these stars, which is more bands than exist for almost any supernova progenitor. The problem is you do have to wait for the supernova to fade, because in general, because it's ground-based data, in the direct images you have before the explosion, the crowding is so severe that you can't do good photometry of the progenitor. You need to wait for the supernova to fade, and then you can use the magic of difference imaging to get rid of the crowding. And so, in this negative image of the 11DH star which exploded, we have something like 100,000 counts. Okay? And so the photometry you can get of these stars is really a calibration-limited exercise once you get to this late time. The other thing you can look at is the variability of progenitors. This is interesting because there's a bit of a bandwagon right now associated with pre-supernova mass ejections. Traditionally, the most common one is that in particular what are called the type 2N supernova, where they show narrow lines. And the picture here is surrounding the supernova, you have a dense circumstellar medium, and the expanding shock wave photoionizes the pre-existing medium and produces the narrow lines. If this medium is dense enough, then what you can do is you can tap some of the kinetic energy and turn it back into luminous energy. So if you remember, there's 10 times as much energy in the kinetic expansion as it's going to radiate. But if I can take that expanding material, slam it into material of sufficient density, I can turn some of that kinetic energy back into heat and boost the radiation. Okay? And so you get these superluminous type 2 supernovae, which could peak at 10 or 20 or 30 times brighter than a normal supernova, and the picture is this. And the question is to do this, you need to have something like a solar mass of surrounding material. And so if you turn that into what sort of winds you want, you're talking wind rates of 10 to the minus 2, 10 to the minus 3 solar masses per year. However, the sort of bandwagon has expanded, and there's a party line growing that lots and lots of otherwise normal supernova have dense circumstellar media. And this is something we can probe from the variability of these progenitors. So while I can't tell you the luminosity of the progenitor until the supernova fades, I can tell you how much it varied, okay? Because that's looking at the changes in flux, which I can get from the difference images, rather than the DC flux, which suffers from crowding. Okay? All right, so we haven't had any two ends go off, so we don't in the sample, so it'll be interesting to see what happens, but we have had a whole bunch of 2Ps. And remember, the picture people have in mind is basically eta car. Is, eta car, for some reason during the Tyler administration, I'm sure it was Tyler's fault, decided to kick out about 10 solar masses of material, which you now see as this dumbbell-shaped material. And so the picture of these very luminous type 2s and sort of ones where you would go down as you scale it down is if eta car blew up now, right, you would have that star ejecting material plowing into all of this, and you would have quite an impressive sight. Actually, it's sort of funny, is even with Assassin, we can't actually do photometry of eta car. It's too bright. It's, in fact, there is almost no monitoring data on eta car anymore because there are no telescopes small enough. So, anyway, there are various pictures about how this might occur involving wave. Elliot Courtard is very keen on some wave coupling ideas. There are some nuclear burning ideas. All right. So we can take the progenitors of the supernova and we can look at how much they vary. Okay, and so this is 17 EAW, okay, which is in NGC 6946. It's actually in the same galaxy as the failed supernova. NGC 6946, it's called the fireworks galaxy. It's the complete outlier. It's had like 10 supernova in the last century, and I think the next runner-up is 3. So it's a bit of fluctuation. But here's the variability of this star over about 10 years before it exploded. And the scale here is 5,000 solar luminosities.